My name's Nick Davey. I'm a product manager with the Contrail business unit. And as soon as my slide, there we go. Today I'm going to be talking to you about Contrail Multicloud SDN. And we're going to take a kind of a dizzying journey. We'll start nice and high level, framing the problem with all of the lovely animated slides I'm sure you've all seen before when discussing multi-cloud. I'm going to dive kind of directly into exactly how we realized that vision, and then at some critical points, I'll show you some examples of that. Obviously, feel free to ask questions and jump in if something doesn't make sense. So what businesses are really looking for when they're consuming multi-cloud is to not have to adapt their processes, their tooling, their code when they move workloads across cloud infrastructure. This is always going to be a balance. And the most bad answer is aiming for that least common denominator. So I know I can get networking from Google, Azure, and Amazon. I know those networking capabilities differ. So in order to ensure that I have a consistent experience, I degrade all of my capabilities down to a common level. That's no good. What we should be aiming for is adaptability. We want our tooling to change, to adapt, and to fit the cloud that our software is deploying in. And so in order to do that, we need to leverage common interfaces for application delivery, common interfaces for network delivery, and common interfaces for security policy definition. We just need to pick who we trust most. What's driving the cloud experience that folks are actually looking for is, I would argue, application owners now. Infrastructure is an afterthought. So as awesome as it is to see what's going on behind the scenes, and we learn a lot from exploring infrastructure, what our businesses are really looking for is to deliver reliable workloads, to be able to optimize for cost, to make it simple to operate and manage, and simple to troubleshoot. And that's without compromising on any aspects of security or control for our traffic. So this is where a whole host of tools have been proposed to satisfy these requirements. And each of these tools tends to be fairly domain specific because it's easy to optimize within a domain. I can very easily image and stand up workloads inside of a data center. I have big networks. I can just throw traffic around, standing workloads up and down. I don't need to think too hard about how I'm imaging stuff. Transfer over to the public cloud. That doesn't really work anymore. If I have a whole bunch of images in my data center, I can't just throw those up into the cloud by magic, right? Similarly, if I'm managing firewalls in my traditional enterprise data center, I have my firewall management tools. I have all of my infrastructure tooled up for my big physical firewalls. When I migrate that to the public cloud, my firewall is now widely distributed. It's essentially connecting to every network or every workload, and I can define those policies very, very differently than I'm traditionally able to in an enterprise data center. Where all of this kind of falls apart, all of the rich tools we have in each domain, it doesn't work when we try and tie everything together. The private cloud strategies don't work for public cloud deployments. So we end up layering more and more tools on top of all of this to glue all of these various private cloud and public cloud technologies together. And here I am with more glue. No, just kidding. Juniper is an infrastructure company. Derek said it best. We're putting networks places you probably wouldn't expect. One of those places that I think has been a little bit unexpected, even though we've all kind of known this for years, is the access network has moved on us, right? Where we plug in our end stations is no longer a top-of-rack switch in a dusty closet. The access layer actually lives inside of the servers. It lives inside of the public cloud infrastructure. Or it lives inside of our managed cloud instances or our managed cloud implementations, depending on the tools that we choose. Contrail SDN is an overlay SDN solution that plugs into the infrastructure at various places to give you that common networking substrate for all of your cloud deployments. So we have a lot of experience working in private clouds across data centers, across telco WANs. And what we've noticed is just like the access network kind of changing on us, what we perceive as the data center underlay, or what connects all of our workloads together, is changing on us. And that's happening as a function of those workloads kind of moving and expanding out across our infrastructure. Thank you for not making the requisite SDN joke at the beginning. Contrail's been a solution in the market since the original SDN land grab. We feel like we've always had a very focused use case and a very central concept to how we achieve our success. And that is we're an overlay SDN solution. So we build tunnels. We firmly believe that the network state, all of the workload and application-specific connectivity and security policies should live as close to that workload as possible. So we distribute all of the state and the complexity for the individual workloads out to the edge while centralizing the control and configuration of all of those deployments centrally. What does that practically look like? So just looking at the over-under view of a traditional SDN-enabled data center. In the bottom, we've got a whole bunch of servers connected together by a whole bunch of switches. At the top, we have these logical concepts of how we want our networks to look. I've got application-specific networks. I don't really care where they are. It's high level, right? So I just draw clouds. I plug my workloads into them. Again, I don't care where those workloads are placed. I'm going to figure that out later. And I dictate my connectivity and my security requirements. Contrail's responsibility is to map those connectivity and security requirements onto the infrastructure that's actually going to host the instances. So as the instances come up, they get all of their connectivity, security, and all of their other traffic steering or flow awareness policies. And that happens at time of workload connection. OK, so what do we get for that? Well, first of all, like I said, this is the new access network. So we get a very feature-rich first hop switch and router. That means that every workload that we deploy, when it's connected to Contrail, has that full benefit of distributed security policy enforcement, distributed routing, and distributed services. It means we can see every packet and frame that comes out of a VM. So if we're doing, for example, security policy enforcement in the same broadcast domain, aka microsegmentation, we can do that by inspecting the local frames and packets for that particular subnet. As traffic's moving through our application delivery environments from subnet to subnet, we can construct the usual types of routing policies that you'd expect, right? Take routes from here, put them in there, now my applications can talk. Because we're dealing with a flow-aware SDN data plane, we don't need to think just in terms of networks and prefixes anymore, though, because we have visibility into all of the application headers. So we can write our connectivity policies around the actual application traffic flows that we want to permit. So if we have a web front end going to middleware, oh, sorry.
Sorry,
Yeah.
Sorry to interrupt you, but just a couple of questions. One on the actual infrastructure here. Are you programming each cloud provider or local on-prem sort of edge infrastructure to provide these tunnels, or are you deploying virtual appliances and building tunnels between clouds and where these different pieces live?
So we've got a couple different models that we can use. The more traditional model for Contrail is to use a software data plane that inserts inside of the guest. So in typical orchestrated compute environments like OpenStack, Kubernetes, VMware, we'll put a data plane into the actual hypervisor or container host, and that'll provide all of the first hop switching, routing, and security policy enforcement, and then build tunnels to the rest of the infrastructure. When we're aggregating connectivity back from a whole bunch of, say, VPCs, we may need to orchestrate the configuration of a big gateway or appliance to aggregate all of that encrypted connectivity. So then we'll apply our configuration and logic to that gateway device.
So within, say, an AWS example for a VPC, there's no user-defined routes, so all that traffic will happen locally unless you're programming the routing of those individual EC2 hosts. So would you deploy an agent in that instance, or how do you kind of do that east-west traffic or programming between things within that VPC?
So for the ultimate in visibility and security policy enforcement, it's best to have something running. You can call it an agent. Actually, we do call it an agent. The control plane element on the host is the Contrail agent, and it's responsible for doing all of that local configuration and policy state. If you don't want to mess with the guests, and that is a hard requirement sometimes, then this is where we will insert something into the VPC to provide that first hop routing, but then you lose the ability to have traffic control in the VPC, and you lose some of the ability to, say, encrypt traffic workload to workload just because you don't have anything in the workloads anymore.
Are you doing anything with sort of transit gateways, say, within AWS to kind of meet that hard requirement, but then separate different things between, say, subnets within a VPC?
Yeah, we'll end up mapping our deployment onto concepts like transit gateway. We don't have any firm opinions on how to deploy things. We have reference architectures, so when customers need that type of traffic flow, we say, okay, these are the sets of features you should consume. This is what you should turn on in Contrail to make it happen.
Okay.
Yeah.
So you're saying the default position is not to insert something into the data path at a network level within the cloud. It's all done at the guest level, correct?
So there's both. Inserting a data plane into the guest tends to be more feature-rich. You get more control over traffic, and you can encrypt traffic between guests inside the same VPC or inside the same local network. But we all know there's some operating systems, there's some workloads. There's just some deployment scenarios where vendors will not be trusted to insert software into that running guest. So in those scenarios, we'll use first hop gateways like the multi-cloud gateway and the VPC.
So how do you go about inserting external components into the data path without compromising availability versus what is natively available in, say, AWS?
If we're inserting the data plane into the first hop VPC network, so we're just acting as a router, we'll control failover between multiple high availability first hop routers. So we'll run multiple multi-cloud gateways, and then do a little bit of magic in the back end, synchronizing both state and checking for availability of all of the gateways in that particular VPC. If we detect a failover, we'll pull one of the routes down and promote one of the available alternatives.
Okay.
It's a little bit easier in orchestrated compute. Like if we're using something like OpenShift in Kubernetes, if the node goes away, the control loop's just sorted out for us, and we find another guest automatically, which is hopefully part of what I'll show you a little bit of later. Okay. So yeah, I was mentioning that we can actually control the flow of traffic. So this is where our flow-based routes kind of start showing, because we're not writing routing policies anymore. We're writing flow policies. We're saying TCP traffic destined to port 443 is permitted between these two virtual networks. That's a routing policy, right? But it actually only matches on the individual flows that are supposed to be permitted between the application layers. And most importantly, what's going on in the bottom here is my orchestrator has tossed my computes to various, my workloads to various computes in the data center. My VRouters, when they notice those computes spinning up, will establish tunnels between all of each other dynamically. And so I'll have reachability between all of these workloads without any configuration changes in the underlay. That's kind of important in a data center where we have workloads moving around and migrating. That's super critically important in the public cloud when you just don't control any of the infrastructure that connects you to your workloads. There's one final trick that we have up our sleeves when it comes to policy control of traffic, and that's redirection or rerouting traffic. This is the old filter-based forwarding, policy-based routing, re-envisioned as service function chaining, and lets you dynamically insert services. What that really means is that you don't need to manage long ACLs and port-based configuration to redirect traffic anymore. Use that same high-level set of policy constructs to grab the traffic you want, whether it be particular flows or all of the traffic from a virtual network, and you redirect that through a service function. Service functions are going to be any middle box that you're familiar with. So that'd be network services like firewall, NAT, content inspection, could be even compliance enforcement, right? We don't really care what the service function is. We plumb the connectivity going in and out of the service functions. That's it. Whatever's going on inside of that thing is the vendor and the customer's responsibility. And that's simply because we wouldn't ever be able to fully grasp all of the things customers are looking to do with those service functions. So we have clean separation at that point, just like any other network device. Drilling down a little bit deeper into the infrastructure, like I mentioned, all of the configuration and analytics is run out of our centralized Contrail Controller. So somewhere in the infrastructure, whether it be private cloud or public cloud, you're going to have a little cluster of these running around. They're responsible for all of the configuration, whether it be programmatic through an orchestrator or just configuring the actual state of our services manually. That configuration is stored in Contrail's controller until a workload in that network gets instantiated. At that point, Contrail swings into action and provisions all of the networking, forwarding, and security policies on that particular endpoint for that particular guest. So the important thing here is that your network doesn't, or the state of the controller doesn't grow with the number of workloads that it's managing. So if you have 10,000 workloads you're managing and you've got a small compute up in AWS, only the state required for that one workload in AWS will be present on that AWS VRouter. So you're localizing state, centralizing control, and distributing forwarding. Yeah.
Is that purely a push model where the controller is pushing down the config, or is something on the endpoint checking in with the controller to say, hey, do you have a new config for me?
Yeah, big ears, right?
Yeah.
So we listen on lots of message buses. That's typically how we integrate with orchestrators, is we will find the message bus where all of these events are taking place, we'll listen to it, and then we'll take action on those events. And that asynchronicity lets us scale very, very well because we're not going out and poking and prodding stuff all the time.
But yeah, the more devices you have, the bigger your controller needs to be if you're pushing down.
Yeah, in this case, we just need big ears, right?
Right.
Which I obviously have.
Is that controller component VM-based, container-based, optional, could be an appliance? Sort of what's the deployment methodology there?
We don't particularly care. It's whatever works for the customers. So inside the controller, there's no special handling required. It's just a bunch of Linux software. Okay. That Linux software used to be a whole bunch of RPMs and debs on a server. It's 2019, so that's a whole bunch of containers now.
Okay.
Right, but I mean, frankly, we don't care where they are. We've done some really neat stuff. We're in a bit of an odd place as an infrastructure SDN solution. When we deploy our containers, there's stuff that they have to do to the operating system more than your typical container workload. So there's a set of privileges that we need to kind of flag off to let our containers interact with the operating system at a bit deeper of a level. Where I'm going with this is, other than that special requirement, you can put those containers anywhere. So we've done demos where we host the controller in GCE. Lame. It's just a VM. Then we switched everything over to GKE. OK, that was a little bit more cool because now we're using somebody's orchestrator to dynamically heal and scale our controller. Now I don't need to worry about things anymore. I like having no things to worry about.
Yes.
So yeah, no opinions on where that lives. It just needs to live somewhere.
OK.
The data plane element that goes into the servers, EC2 instances, container hosts, that's our VRouter. So the VRouter's responsibility is for listening to those messages on the message bus, interacting with the controller, getting the policy state and configuration for that particular workload, and then establishing all of the tunnels. The VRouter does all of the actual hard work, the heavy lifting of forwarding or filtering traffic and generating analytics for every flow that it sees. And where that VRouter lives, I've talked a little bit about. It can be in your VMs. It can be in your container hosts. It can be your gateway for your VPCs.
So what kind of overhead is associated with that?
Depends. How fast does it need to go? So it's a software forwarder, right?
Yeah.
Feed me CPUs. When you're doing typical enterprise workloads, there is a very limited overhead. We operate in an interrupt-driven forwarding mode. We don't reserve CPUs. And we can still get very, very respectable performance out of that model. This being Juniper, we tend to have a very service provider focus, a very telco focus at times. So that forces us to address telco-sized problems. So when folks are modernizing their services infrastructure and moving their actual appliances that used to be this big into servers that are this big, we need to replicate some of that forwarding logic that those line cards used to enact. For that, we use user land forwarding extensions like DPDK, which does carry a significant overhead. That means in DPDK, in particular poll mode, you have a CPU just sitting there spinning saying packets, packets. And how many of those forwarding threads you have is just a function of how much performance you need. So we've got scaling numbers that tell you how many cores get you how many packets, and we've even gone down to like the nuances of hyper-threaded sibling cores and stuff like that to show people what the actual trade-offs are and make them aware of kind of what they're paying and what they're getting for it.
OK.
Could that be run on a FPGA or some sort of specialized NIC as opposed onto the processor directly?
I did not pay for that lead.
That?
Thank you very much. Great setup. I love it when a good plan comes together. Where can we jam the VRouter? So yeah, this is the new hotness, especially in high-end software-defined networking. It's taking the software data plane and cooking that into something like an FPGA or some kind of dedicated set of coprocessors for packet processing. Mm-hmm. I say the new hotness. It really is the new hotness. Like we're kind of bouncing it from side to side, figuring out how this is all going to work. Juniper has a set of partners, Metronome, Mellanox, Intel, folks that we work with to understand the space. We've been building prototypes. We've been building these capabilities into our products and seeing how that changes the overhead cost for our telco customers. For enterprises, we tend to get fairly reasonable performance, and enterprises don't tend to be asking SmartNIC questions unless they have very specific use cases. Telcos, on the other hand, it's just bigger is better, right? They're replacing something this big. They want as few servers as possible, and SmartNIC makes that happen.
Sure.
What's been blowing my mind is how cheap these things are. Like it's not like purchase order and wait. It's more like swipe your credit card and receive the next day.
Wow.
So yeah, I was pretty impressed. And then, yeah, the other two models I've talked about, right? Virtualized compute, and then the VRouter on bare metal doing all that DPDK stuff. So where else do we go? Public cloud infrastructure, that's kind of what we've been talking about today. So the first hop gateway for your VPCs, when we can't interact with the guests, well, we'll deploy something that kind of looks and smells like a router. And then finally, we have to get traffic into and out of all these overlays. Tunnels have entrances and exits, well, if they're good tunnels. So to get traffic into and out of our overlays, we can use software gateways and software devices. In larger data centers, larger enterprises, we can use hardware gateways and hardware devices as well. Fortunately or unfortunately, we don't have like the Contrail branded next generation SDN gateway. Instead, we picked a set of standard protocols. Networking devices speak networking protocols. We're a networking company, so it all just kind of made sense to us to use BGP and EVPN when we're going to be passing around MAC address routes and reachability in our cloud, right? And then we can use VXLAN as a tunnel. And now suddenly inside of my magic SDN data plane, I have a encapsulation that every data center switch practically can terminate. I really did pause before putting this slide in there. It's a little too on the nose. It's like an MPLS router company. This is something kind of weird and kind of cool that we do, though. Because VRFs in enterprise operating systems, the concepts of network segregation in an enterprise operating system is relatively rare. It's fresh and new. VRFs only got added to the Linux kernel very recently as the trend of white box switching has been rising. We've been doing this since 2012, so we need to kind of do our own thing. So what we did is inside of our software data plane, we actually wrote a set of VRF semantics so we can attach workloads to their own dedicated layer 2 and layer 3 forwarding tables. This is a little bit different than firewall separation for workloads, right? Because we know we can plug in two kind of dissimilar guests into the same switch and use a firewall to make sure traffic doesn't go between them. But it's better if they could just never talk in the first place. You know, why have a default permissive model that you then control with policy when you can actually just break the connectivity in between two separate guests? So this has been a big advantage for us. It gives us the ability to segregate workloads on a network level inside of the host. So never the two shall talk.
Is that only KVM-based hypervisors, so that you're not going to support ESXi or Hyper-V, putting at the Linux hypervisor kernel level?
So the kernel module itself plugs into the Linux kernel. When we need to interface that into non-Linux systems, what we'll tend to do is run a lightweight guest VM, connecting using either SROV or PCI pass-through to the underlay network. And we'll plumb all of the guests into the data plane using the native switching infrastructure of that particular hypervisor. Does that make sense? That felt circuitous as I was saying it.
But here you're talking about the so this is KVM based where you're plugging into.
Yeah. So picture in a VMware scenario or any non-Linux hypervisor, picture this being as a guest VM, and the vSwitch inside of that non-native hypervisor is going to provide these crossover cables, the tap interfaces. In Linux, we use a software interface that acts just like a crossover cable to plug guests into the VRouter. We would use a dedicated slice of a hypervisor's vSwitch to do this in environments where we can't interact with the kernel. The other option that we have in those scenarios is to just orchestrate the network connectivity. So we can either put it into the VM in the hypervisor or kick it down to the network and manage it with config.
But you were saying you're doing separation at this level here. So in the model in a VMware environment, you're plugging into the vSwitch, and then are you then expecting everything to connect into the kind of port groups that you're managing through this infrastructure to maintain that separation?
So we implement, using that listener model, a set of actions in the back end to map a whole bunch of private VLANs through dedicated vSwitches, so the guests still can't talk, even though they're on shared infrastructure inside of the hypervisor.
Because you kind of take over managing the virtual switch environment within a VMware environment. Yeah,
you have the option to mix and match administration of some of those vSwitch components. Generally, it's easiest just to let the orchestrator do it for you, but if you have strong opinions about the way things need to be plumbed, you can definitely get in there and do that.
Do you have any opinion on if there's other things in your environment that also need that requirement to be programming, like distributed switches? So say VxRail or Cisco ACI and VMM, they're relying on being able to program the distributed switches as well. So if you're plugging into that environment, you're not going to have exclusive access to be able to program that VDS.
Yeah, so we're going to carve out our own set of resources that we use for connecting the virtual machines to the specific data plane, right? We don't need to use VDS because we're distributing connectivity between all of the hypervisors in the Contrail VRouter. We just need to isolate, really provide that crossover cable experience in the hypervisor.
You create a standard vSwitch for every kind of host and then plug into that yourself that way?
Yeah.
Okay.
This is one of these areas where we've been shut out of kernel networking ABIs. We're really looking forward to SmartNICs to save the day here. So we don't need to run a data plane in software if we can put it on the network interface. The component, that agent that sits on the, I even have it in the picture. Yeah, so that's the agent. Agent's just a piece of user-line software. We actually can run this on a container and then have it remote program a data plane, like in a SmartNIC. So, I mean, talking conceptually and stuff that we're working on, in an environment where we couldn't insert a data plane into the kernel, we would have an agent running in a container just happily chirping away, listening to the orchestrator messages, and then programming the SmartNIC to provide connectivity using either SRIOV virtual functions or, again, relaying through some kind of native vSwitch. Does that make sense?
Yeah.
Should I even ask about Windows hosts?
That answer was exactly for Windows hosts. So if I had a third thumb, I would give them 3 thumbs up for Windows containers. Microsoft has done an incredible job modernizing its operating system. Windows containers actually hit GA with Kubernetes 1.14. Mm-hmm. So laziness is next to godliness. We don't need to port software if we can run Linux containers on Windows. So the agent, we can tuck happily away running in a container. The data plane, then we have either the software data plane that we've written to insert into Windows or SmartNIC. Okay. Again, for a lot of options when you need real portability in the data plane, SmartNIC is going to be a real advantage.
Right.
Especially if this goes the way of like sound cards.
Mm-hmm. I think it might.
Cross your fingers too, maybe it'll happen.
Double crossed.
I talked a little bit about the control plane containerization. I won't belabor the point on this because you guys asked it already. Really, containerization for us means 2 things. It means that portability of not having to worry about where our stuff runs. You can either run it in a VM or decompose the containers out onto native container hosting platforms. The funky thing for us is that it's easy now, or easier, I'll say, to install complex Linux software. All of the dependencies, everything that software needs to run is now lovingly bundled up into that container image, and we can roll that out on any Docker-compatible or CRI-compatible container host. So we don't need to worry about, please install these 10,000 packages before you install Contrail. Instead, we can say, grab this container and have a great day. That also makes scaling easier for us, and upgrades, right? So we can just deal with our services now as atomic elements. Running out of config scale, every time I hit the API server, I'm waiting longer and longer and longer. My environment's growing. What do? Spin up another config container and load balance them, right? This gives us easy tools to solve hard problems. So I've used the K word a lot. I started off by talking about how hard it was to deploy applications across dissimilar cloud infrastructure. And the way that I at least frame the problem, and I hope it made sense to you folks, is that when we're consuming native services, we have to retool our infrastructure as code, we have to change our automation workflows to adapt to each public cloud, or we have to adopt a tool to do that for us. Kubernetes is one of the proposed solutions to provide a common API for the delivery of cloud infrastructure. And from that simple sounding mandate, it's reaching up and down into all kinds of weird places, and we're finding it in environments that we never thought we'd see it. But it acts as that neutral API that doesn't take away any of the capabilities of the cloud platform. Actually, Kubernetes has a really great model, one that Contrail has followed. A load balancer in Kubernetes is a load balancer. You define it, you configure it, your application developers manage it like they would any other Kubernetes load balancer object. What happens in the background is the cluster is configured to implement that load balancer object differently depending on what infrastructure it's deployed on. So if I have an AWS Kubernetes cluster, my load balancer will actually turn into an ELB. If I'm running in a private cloud, that load balancer will actually be a /32 route that gets advertised to my SDN gateway. And Kubernetes and the networking componentry inside of it is responsible for that adaptation. Kubernetes has one, we'll call it minor flaw, and that is the complexity curve, the learning curve of seeing all that YAML. James Kelly introduced me to this the first time and said, it's so simple, look at the configuration for this one service. Scrolling, scrolling, scrolling through lines and lines of curly braces. I kept thinking to myself, where did this come from? Where did this madman come up with this design? Like, who told him this is what a pod should look like? And slowly, we've all been exploring Kubernetes and figured out how we can tease those details out. Now we know not to be afraid of the curly braces, and life is better. But it's still a terrifying jump to make. And that's where companies like Red Hat have brought in OpenShift. So OpenShift is the friendly container platform that gives you the same set of concepts, not surrendering a lot of control for that simplification of the Kubernetes interface, but gives you something that's maybe less scary, less YAML-y, if that's not a word. It is now. Thanks. So whether it's upstream Kubernetes, whether it's somebody's hosted Kubernetes, or whether it's OpenShift, the way that you integrate into all of these ecosystems is really harmonizing around common cluster infrastructure and that concept of adaptability, right? Figure out the right way to implement this configuration in this particular Kubernetes cluster. And then why are people deploying OpenShift? Like I said, it's the friendlier, I'll say friendly. It's the friendlier alternative to a lot of CLI, to a lot of YAML. It also layers on top a whole bunch of really funky stuff like day 2 problems that you'll get after you stop being afraid of Kubernetes and start trying to do stuff. You're going to quickly run into problems like, where do I host my containers that I just built? I'm really proud of this thing. Where do I put it? So it comes with a set of high-level tools like container registries, like CI/CD pipelines, things that developers can directly consume. The neatest thing that I've seen, especially from a demo perspective or from a user and developer perspective, is that OpenShift actually has a set of high-level tools that let you plug into your text editor. So you can use a plugin in Visual Studio Code to actually push your code directly to OpenShift to have it build container images for you and run those container images automatically through their source-to-image implementation or feature.
Do you only support OpenShift, or you also support native Kubernetes as well?
Yeah, native Kubernetes as well.
So, okay, so you're talking about the value of OpenShift and presumably a partnership with Red Hat for that piece. But
absolutely.
But you do support native Kubernetes as well.
Absolutely. And actually, we started in upstream Kubernetes when we went down this road. We actually took a really long time to figure out what the right way to simplify the Kubernetes user experience was. And we looked at various solutions in the marketplace and waited for things to kind of congeal before we jumped in with our old favorite partner, or one of our favorite partners, Red Hat.
So in terms of maybe I missed it, but in terms of what you're adding to Kubernetes, is it programming access controls between containers, or managing the load balancer, or doing kind of IPsec tunnels between Kubernetes clusters? Okay.
I don't want to gloat too much, but I do really love when a plan comes together. Because I showed you all this VRF stuff before, all this security policy stuff, and you wondered why is he babbling. The reason for that is all of these concepts become super important when we're dealing with things like containers that are sharing critical operating system componentry, right? I heard network namespaces referred to as like the room dividers the other day. Like they don't provide isolation, they provide the appearance of enclosed space. Punch the paper divider in a room and your fist goes right through it. Similar to network namespaces sometimes. We provide that VRF level isolation within Kubernetes now. So when you have pods that are supposed to be isolated from one another, say in a particular namespace, that namespace can be turned into its own VRF, and you have now network and reachability level isolation. That means you can't ping, there's no firewall, there's just no reachability. Most importantly, it means you can start having overlapping resources. So if your developers say, oh, no, this is the magic IP that my application always hits, it has to be in dev and in prod, well, the really easy way to make sure you never accidentally cross those streams is to make sure the dev and the prod reachability can never talk, right? So I have the same IP floating around everywhere. I can consume it from any point. It just depends on where I am. Is my test user in dev or is it in prod? That IP will respond differently. So we can do some cool tricks with this level of network isolation. The other neat thing that we did is and this has been kind of a theme with Contrail, is we mapped this into the native orchestrator capabilities. So yeah, sure, go to our web interface, use our API, do whatever you want to configure your services. When you hand this over to your application developers, the first thing they're going to do is submit a whole pile of requests back to you about what they want changed. So what we've done is we've exposed a lot of the Contrail specific things, things like VRF isolation. Do you want that, or do you want just common reachability? That's now a flag in the Kubernetes pod manifest. You can use the Contrail custom resource definition to say, do you want VRF isolation? Should you NAT all traffic out of every host, or do you want to aggregate everything back through a central firewall, right? What's your threat model like for outbound traffic? You can control all of that through Kubernetes as well. So if you really trust your developers, you can hand control of VRF creation, security policy, like firewall policy definition, as well as load balancer configuration, all into the developer's hands.
Does that CRD have any respect for RBAC that you may configure within Kubernetes to say, like a kind of more granular idea of that permission example you gave? So I could program certain load balancing rules or security within the namespace that I'm allowed access to, but not for the entire cluster.
Yeah, absolutely. And that's the benefit of using CRDs inside of Kubernetes is the admission control hits as soon as the API call goes in. So it doesn't matter what the CRD is, you just define what the action is that the user's allowed to do. Nobody glared at me when I said that, so I'm assuming I'm at least mostly correct. And like I mentioned, you can flag on and off this behavior. So if you want to let every developer spin up their own environment, but you really want to make sure they're isolated, you can have the default behavior be namespace isolation. Every time you create a namespace, you get a VRF.
Yeah, we installed a landing script here. That was...
I thought that was my rolling thunder. Yeah, so you can flag that behavior on and off. So every time a new developer creates a new application, new VRF, new reachability, go play. Or you can have that in your production environments be a controllable flag from the developers. You know, I always want to push to prod, but every once in a while I want to use a flag to wall this off for dev. And then finally, you can just go nuts with policy and create your own little custom isolated islands around objects. But you said we were talking about multi-cloud. So yeah, this is when it comes back to that whole concept of overlays and tunnels, right? Because when we're creating tunnels between things, the type of infrastructure that we're riding on top of should inform the type of tunnel that we're using. If we're going over shared untrusted infrastructure, we need to use encrypted tunneling. If we're going over just data center private connectivity, well then I want as fast as possible. And I can flag on and off these features on a per VRouter basis. So I can say this set of VRouters or this particular VRouter, which is a compute endpoint, this is in a trusted space. Any traffic heading over to this VRouter should be completely unencrypted. This pool of computes is over in AWS. We don't trust the infrastructure connecting us to AWS, so flag on encryption for all traffic destined to those VRouters. So you get selective application of encryption. You're not encrypting stuff that doesn't need to be encrypted. And then the other thing we're doing is stitching up all of the connectivity between all of those multi-cloud gateways. So the first step to having an underlay is being able to ping from all of the stuff connected to the underlay. It doesn't really work well if you have a node in AWS that can't connect to your private cloud data center. So automating that connectivity, I know it sounds really simple. That's actually a huge challenge that folks grapple with as they're adding and removing VPCs, is providing that connectivity, that tunneling, and that policy control back to the private cloud infrastructure. I can't believe I've been talking for 40 minutes. This has gone by in a blur. I'm going to flip over to one or two of the demos. We'll conclude there, and if we get a little bit more time, I'll talk about some funky stuff that we're doing. And of course, feel free to interrupt questions. So I worked with our TME. OK, it's showing up there. I worked with our TME team to build a series of demos to highlight the capabilities that I talked about today. Practically everything you're seeing, especially depending on how fast I talk, is stuff that you can do right now in Contrail. So no matter what I'm going to end, please remind me, Lisa, with my call to action to try this stuff out. And you can go out and consume all this stuff yourself. So what we're going to demonstrate in this very, very short video is connecting up to a brand new AWS infrastructure. I have my San Francisco private cloud. I've spawned up a whole bunch of containers in my private cloud. And once that's all up and running, I want to start migrating stuff over to AWS. Ideally, I want to do that with the same management surface. Ideally, I want to do that without making any changes. So actually, this is going to be really, really hard to do from here. I apologize for this. I thought I was being a genius when I got this all worked out, as usual. Yeah, so critical in Kubernetes, and this is kind of a funky requirement that nobody really understands until they try and build this stuff across infrastructure. Kubernetes assumes that all of the nodes are going to be able to talk to each other, which in a data center, that's a pretty safe assumption. When you're running in a multi-cloud deployment, that is not a safe assumption at all. So these workloads are going to be handing out IP addresses in that flat namespace, that flat subnet, and we need to provide reachability. That's the job, the number one job of SDN in Kubernetes, is making sure all of the pod IPs can talk. You don't do that, you haven't done anything. So we've got our service IPs that we've exposed. We've got our pod IPs. The first thing that we're going to do, I believe, is test out connectivity. And so there's our app there. This is the cheesy, cheap, and cheerful. I think this is actually getting cut off as well on my screen, so if you'll just excuse me for a sec. So for anyone wondering about some of the other benefits of OpenShift, to help developers, they've actually put together a really funky click-through application development using a library of applications. So this, here we go. Now I can do this. So that store application where it's just clicking through and purchasing like a camera, this is a default application inside of OpenShift. So this is why you usually see the same flow for a lot of OpenShift demos. It's just an easy click through. Where we're transitioning to now is over to AWS. And I've got the nodes running. They're not joined to the Kubernetes cluster yet. So what we need to do is use our Terraform automation to connect these. So first of all, connect the multi-cloud gateway into the cluster. So that's what we're going to kick off here. We can't ping the node yet, but once our tunnel comes up, and I mean, you can always sniff out on-demand tunnels out of sequence, high latency on the first packet. These get formed dynamically upon traffic generation. So the first packet that hits our AWS cloud, tunnel comes up, our underlay has connectivity, and now we can start spinning up workloads. So the next thing we're going to do is run our script to connect all of my AWS workers into the Kubernetes cluster. And then once they're part of the Kubernetes cluster, I can see I've got my brand new nodes that are coming up. Slowly. There we go. So once my nodes come up and report as ready to roll to Kubernetes, I can start moving pods around. So two things have kind of happened quietly in the background, is that the multi-cloud gateway connected itself back to the private cloud data center using an IPsec tunnel, and that formed up the basis of the underlay. If you had EC2 instances that you just needed connectivity for, stop here, right? You're good. You can ping in that encrypted overlay. You have connectivity to your EC2 instances. Your job here is done. If you're doing Kubernetes, there's more work. You need to join that to the cluster, just like we did. And then once those nodes are available, then we can start throwing workloads on them. So this is really subtle. But if you take a look at the node name on the far right side, you can see that app that we deploy. And sorry, I can do cool stuff like this now, right? Yeah. If you take a look at the node name, you can see that app that I was just running in my private cloud data center has just respawned out to 3 AWS nodes, right? Nothing really happened in the background. Normally, I keep a web browser rolling just to show you that you can keep clicking through the app. This is, again, one of these benefits of Kubernetes. The applications tend to be stateless, so you can shoot them in the head, and they come back, and everything still works. What is Contrail actually providing here? I mean, I showed you that ping, the weird high latency, dynamic tunneling's fun. What do you actually get? So every packet that goes through Contrail generates a flow analytics record. And that tells us a number of things. It tells us the node that it came from, the IP that it came from, the guest that it came from if we're orchestrating that compute, and then all the information about where it's going to. So in these types of scenarios where we're connecting to VPCs, we can actually use our analytics information to trace the flow of traffic through the internet into each VPC. So we can see from an underlay perspective here, this is just the nodes sending pings back and forth, right? So this is just pure underlay. If I switch to the overlay view to see traffic through my application, that kind of shopping cart OpenShift thing, I can see the actual application views as well. So that gives me actually 2 kind of layers of visibility. I can see if my infrastructure tunnels are up and if traffic's going over it. And then I can, on a per app basis, watch all of the flows going between all of the components. And this is just built into Contrail by virtue of the fact that we're flow aware.
For those flows, are you seeing sort of layer 7 connectivity? Can you tell what they're doing, or is it just kind of the packet trace in itself?
Depends on the layer 7. So
can you tell whether that's HTTP, HTTPS, or a gRPC, or what's going on?
No, we'll just what we'll tend to do is go up to layer 4 for the flow records. If you need to see the actual application payload and do inspection, you've got 2 options. In Contrail, there was like a door number, mysterious door number 4 that I never talked about. You can mirror every packet that hits the VRouter. So you can just say, clone me a copy, send it somewhere else. Where that somewhere else is, we don't care. It can be a port, a VM, an appliance, don't care. That gives you the ability to rip open the packet and see payload. The other thing that we do, I mentioned a little bit about service chaining. I thought it'd be about 30 minutes forward through this deck by now, but I had a little bit about service chaining, and in particular, container service chaining, which is becoming a thing. When you need application inspection ripping right down into the payload, this is where we can leverage service functions. So we can use something like a web application inspection service function or an IDP IDS service function, reroute traffic through it, and then get all the application visibility from that service function. The cool thing about that approach is if you're not happy with the way traffic's being identified or it's not doing a good job, you can swap out that analytics service function and replace it with another one.
But identifying that traffic at a higher level and getting that detailed insight, which really in this world is kind of where you want to be heading towards, you're having to kind of hairpin the traffic through something else to be able to analyze that. You're not able to get that data from the fact that you're in the hypervisor or in the Kubernetes node.
So yeah, it depends, right? Like for anything that Kubernetes know, we know. Like for example, we can see the workload here is RabbitMQ, we can see Celery, we can see Redis, we can see what the port is, what the node says it is. Application traffic fuzzing, especially if it's encrypted, that's something we can't do in the data plane at speed. In order to prevent the hairpinning problem, what we tend to do is just spin up multiple instances. So you can even get to a scenario where you have like a service function that's also a daemon set. It lives on every node, and that's providing local load balancing for all of that particular application inspection.